As the chairman said, I'm Pasquale Sustana, coming from the University of Bolzano, and this is a work in collaboration with Dr. Cortese and Dr. Nandi, coming from the same university, and with Dr. Boggiato, coming from University of Rome, La Sapienza. Let's start with the motivation. Tailor welded blanks are the most promising solution used in the automotive industry to fabricate resistant lightweight components. In particular, a tailor welded blank is a single plane sheet that consists of two or more sheets that are welded together, generally by using laser welding, before the final sheet forming operation needed to realize the final component. So due to the fact that we need to deform this sort of components, we have to consider that we have several parts of this sheet that exhibit a different formability. Because we can have, for instance, different base metals that are welded together, and then we have to consider that also the weldments exhibit a formability. The formability of the weldments depends on the presence of the fusion zone and of a heat affected zone that exhibit different formability. So, in order to optimize the laser welding parameters that are used for the fabrication of tailor welded blanks, and in order to obtain useful data to implement infinite element analysis of the forming processes of tailor welded blanks, in order to guarantee proper formability of these blanks in the final stamping operation, we need to have the possibility to assess the local mechanical properties of the welded joints that are in the tailor welded blanks. So the digital image correlation can be employed to assess the local mechanical properties of the weldments in tailor welded blanks. Here you can see an outline of this presentation. We have defined the full field strength measurements in some samples subjected to a tensile test by using digital image correlation, considering two typology of steels, of high strength steels that are used for the fabrication of these tailor welded blanks. We have used particularly for the digital image correlation two image graphing systems. Then we have compared the results coming from these systems. And then we have then done a sort of tuning in order to understand better which are the better parameters that can be used to optimize the results coming from these systems. Here you can see briefly which were the process parameters that were used to obtain this laser components. In particular, we have welded dual phase and hot stamping monosteel by welding process. We have obtained this sort of samples to be subjected to a tensile test in order to assess the full strain field in this region. Here there is a picture, but not here. So you can see here a part of the speckle that was covered all the sample in order to apply the digital image correlation. In particular, here you can see the chemical composition of dual phase steel and hot stamping monosteel. In particular, you can denote the peculiar different mechanical property of the two steels. In particular, you can see that the hot stamping monosteel exhibits a very high tensile property with the ultimate tensile test of about 1,500 megapascal in respect to lower value that can be obtained in dual phase steels. Sorry, here. And here you can see the difference about the elongation factor obtained by the tensile test of these iron metals. Here you can see the two cameras that were used for digital image correlation, in particular in one side of the sample, we have used this sort of camera by using a telecentric lens with an image acquisition of 1 image per second that concentrated in particular along the weld seam. Here is a problem about the picture. And then we have also used a commercial reflex camera that instead viewed a large part of the samples, considering all the edge length of the specimen. In particular, I hope that the video works. Okay, in order to show you in which way the digital image correlation method works. Okay. In particular, we have used a method implemented by Dr. Broggiato, where we have a grid that is on the samples. During the plastic deformation of the samples, we have a modification of the grid, and by knowing the displacement of the node, we are able to evaluate the strength field on the material. In this reference, you can find in more detail the basics of the digital image correlation method that we have used in this case. Here you can see some images obtained at different level load during the tensile test. In particular, here we have 4 images according to the total equivalent strain evaluated on this sample, and here you can see other images related to the true thickness strain. In particular, this is the first image, the second, the third, and the fourth image obtained at different loads, in particular at increasing load. In the upper part, we have the dual phase steel, in the lower part, the standing bora steel, and here in the middle, we have the laser weldments. As you can see that we have an increase in deformation, particularly on the DP side, due to the fact that the steel is a bit lower tensile property in respect to the standing bora steel. And here you can see the same image relative to the thickness strain. Also in this case, I have a video to show you in order to understand in which way the strain field modified during the test. Okay. You can see here during the test the increase of the plastic deformation in this region. Here we have the weldments, and then we have the final rupture correspondence of the zone that you can see. Oh, sorry. In particular, we wanted to compare results coming from the two grading systems. In particular, you can see here a peculiar curve obtained by these samples. In particular, we have defined for 4 loads level the total equivalent strain, the true thickness strain in different parts, in particular along this green path and along this horizontal path. The vertical path is for the most length in the DP side, with the fact that it is still deform a lot in respect to the other steel. Here you can see the results that were obtained for the different load that we have seen here, and according to the different path that we have found before. So here you can see for the different horizontal path, which is the file of the total equivalent strain for the several load in this region, along the weldments and along the standing bora steel. In particular, you can see the high deformation of the dual phase steel in respect to the other steel, and here you can see the deformation of the weldments during the test. Unfortunately, the weldments did not deform significantly, so we have this sort of colors obtained by digital image correlation. Here you can see also the profiles relatively to two constraints coming from considering the constancy of the volume along the thickness of the components. And so you can define also the value of this factor in the several horizontal paths that we have seen before. These are also the same factors that are represented instead along the vertical path that we have seen before. As you can see that along the welded that is located in this point, we have not a significant plus deformation. In the dual phase side, instead we have an increase in the deformation, the several load level, reaching a maximum in the region where the necking occurs. And the similar thing can be said relative to the two thickness strain. Then we have compared the results coming from the two gravity systems. And to do this, we need to do a match between the image coming from one camera to the other one. In particular, we have needed a match of the time in order to have a synchronization of the image acquired. A matching about the magnification. This is not a problem for the telecentric lens, but we operated a scaling for the Nikon camera in order to have this matching. And then we have also matching of the two images, horizontal vertical matching and angular matching of the image in order to have a perfect matching of the two images. And this is the result by considering the grid obtained by the telecentric lens and the other grid obtained by the Nikon camera. Here there is a comparison between the results obtained by the two cameras according to the dimensions, size of the grids that were used during the digital image correlation. Obviously, for large grid, we have a sort of smoothing of the total equivalent strain. By reducing the size of the grid, we are able to have good results by using the Nikon camera, according to the results obtained with the pixel camera. And if you reduce further the grid, we have that in this case some noises coming from the fact that we have very small grids, and so we have these issues. So by varying the grid, we are able to define which is the proper grid that can be used to obtain proper results. And the same was done for the full thickness strain. So concluding my presentation, I can say that we have obtained by using this topology of camera accurate evaluation of strain range by using also proper algorithm developed by Dr. Borgiato. We have used not expensive equipment to do this, so without any sort of high resolution. And then a future approach that can be used to continue this research is to apply this method to other type of laser welded structures, and particularly to define directly constitutive model to be used in infinite element software. And then we can also use this technique in order to tune the welding process parameter that are used to obtain this telewelded plans.